Take a scenario where 1 million users compete to buy exactly 1,000 items. This traffic spike acts like a physical force on your infrastructure. This diagram maps out a standard 3-tier architecture. Normally, traffic distributes cleanly from a load balancer through stateless compute nodes into a relational database. A flash sale breaks this model through extreme asymmetry. 99.8% of requests are destined to fail. The system collapses because this massive wave of requests strikes the database simultaneously. Adding more servers to your autoscaling group does not solve this. You cannot vertically scale your way out of a database bottleneck by throwing more compute at it. A flash sale is an extreme load shedding problem. Success means rejecting surplus traffic as early and as cheaply as possible to protect the inventory state. Alibaba's single stay provides the ultimate physical stress test for high concurrency architecture. In the opening seconds of the event, the infrastructure routinely processes hundreds of thousands of transactions per second. Achieving this throughput with zero downtime requires abandoning standard assumptions about relational data models and ACID transaction isolation. To survive, architects reconstruct the flow of data from the core database outward to the absolute edge of the network. This diagram isolates the central vulnerability, a single row in a relational database holding the inventory count of a promotional item. In a system using optimistic concurrency control, multiple transactions read the inventory simultaneously, calculate the new value, and attempt to update their private copies. When they try to commit, only the very first transaction succeeds. Every other concurrent request fails its version check, forcing the application to retry the transaction and triggering a massive CPU-burning retry storm. The alternative is pessimistic locking. Here, the database places an explicit lock on the row up front to prevent conflicts, but under flash sale load, forcing thousands of transactions to queue up sequentially quickly saturates upstream thread pools. The latency spikes and the entire database engine locks up. This equation calculates the probability of a write conflict, proving this failure is a mathematical certainty. Lambda represents the transaction arrival rate, and T is the duration of the physical lock. When the arrival rate spikes into the thousands, the conflict probability instantly converges to 1.0. Because the conflict probability reaches 100%, persistent relational databases cannot directly absorb flash sale write concurrency. This architectural diagram introduces the solution, pulling the inventory system of record completely out of the database and placing it into a distributed in-memory cache layer. However, executing standard cache get and set commands independently still creates race conditions. Two threads read the same value and write back the exact same deduction, resulting in overselling. To fix this, the application executes a Lua script directly on the cache chart. This guarantees the read and decrement steps are evaluated as a single, fully atomic operation. This uses the write-behind caching pattern. The user receives a sub-millisecond success acknowledgement immediately from the cache, while the database remains untouched. But holding state purely in memory introduces a vulnerability. If the cache node crashes before the relational database updates, the order disappears entirely. To prevent data loss, the system uses an asynchronous message broker, like RocketMQ, utilizing a half-message protocol to safely capture the reservation event. The broker guarantees distributed transaction integrity. It holds the message safely in a queue and syncs it to the durable database in the background at a rate the database can actually handle. Decoupling in-memory atomic processing from asynchronous persistence protects the shared state, ensuring exact inventory counts without sacrificing latency. This diagram shifts focus outward from the data layer to the Kubernetes compute cluster that handles the actual application logic. Relying on reactive horizontal pod autoscaling during a flash sale guarantees a crash. Reactive scaling waits for CPU to spike before booting new virtual machines. By the time they join the cluster, the active nodes are already dead. The system requires scheduled preemptive scaling. Maximum capacity must be fully provisioned and healthy before the sale begins. But even with pre-scaled compute, serving non-essential dynamic content wastes precious CPU cycles during a peak load event. Systems employ bulkhead isolation to prevent one failing microservice from consuming the entire connection pool, dropping strict boundaries between operations. Next, the API gateway executes active load shedding. It dynamically disables non-critical features like search indexing and reviews, reserving all system resources exclusively for the checkout flow. Compute power is a strictly finite resource, and it must be ruthlessly guarded to prevent downstream cache saturation. This diagram pulls back to the absolute perimeter of the architecture, the content delivery network and web application firewall. The cheapest, safest place to reject surplus traffic is at the network edge, before a client ever initiates a TCP connection with your origin servers. To execute this, a virtual waiting room intercepts the incoming herd at the edge and places visitors into an elastic queue. The waiting room issues cryptographically signed tokens to each legitimate session, preventing automated botnets from jumping the queue. It then performs a highly controlled metered release, allowing authenticated users into the storefront at the exact rate the backend architecture can sustain. Edge interception acts as the ultimate load-shedding tool, stripping away the chaos and transforming a catastrophic traffic spike into a predictable stream. This system map shows the complete optimized pipeline operating synchronously under intense load. 100,000 concurrent requests arrive at the exact second the sale launches. 90,000 of those requests are safely intercepted and held off-server by the virtual waiting room. 10,000 requests pass into the compute tier. There, 9,000 are dropped by load shedding and circuit breakers due to missing tokens or unauthenticated states. The final 1,000 legitimate checkout requests execute their atomic Lua decrements in the cache and asynchronously sync downward. The persistent relational database remains entirely protected, processing the confirmed data at a calm, steady pace. Engineering a successful flash sale does not mean scaling processing capacity infinitely to meet demand. It requires architecting a system that survives by perfectly controlling the cost of rejection.